Welcome to CECS 228. This is Graphs Part 2, which deals with special graphs and bipartites. For these set of lecture notes, we're going to be considering simple graphs, and that means that we're just thinking about graphs that are undirected, don't have any loops, or multiple edges. Okay, so we're going to start by looking at a list of special graphs, starting with complete graphs. So a complete graph with n vertices, which is denoted k sub n, is a simple graph that contains exactly one edge between each distinct pair of vertices. So what we're going to do here is draw some of these k sub n simple graphs or complete graphs, starting with n is equal to 1. So if n is equal to 1, that means that we only have one node, and because it's a simple graph, there are no loops, so that means we can't have any edges. For K2, that means that we have two nodes, and that would mean that we only have one possible edge. If we are looking at K3 now, that means three nodes, and starting at this top node, it can have a connection to the bottom left-hand node and then the bottom right hand, and the remainder, the remaining two unconnected nodes could now be connected by that edge, and then this would give us all possible connections between the nodes. If we look at one more, K4, that means we have four nodes, and I'll go ahead and label these so it's easier to refer to them. So A, B, C, and D. If we want to think about all possible connections that can be formed starting at node A can be connected to B, connected to C, connected to D. Then looking at B, it could be connected to A, which it already is. Then it could be connected to C and to D. Then focusing on node C, it can be connected to A, B, and D. And then finally, D could be connected to A, B, and C, which it already is. So that would be the graph of K4. And we would just repeat that process for any integer greater than that, any given number of nodes. Let's take a look at cycles now. A cycle, which is denoted as C sub n for n being greater than or equal to 3, is a simple graph that consists of n vertices and the edges v1 with v2, v2 with v3, all the way down to v sub n minus 1 with vn. And we'll draw a few of these. I'll start with C3. So C3 means we have three nodes. Let's just go ahead and call them v1, v2, v3. And in this case, we have an edge v1 to v2, v2 to v3, and there's actually one more edge that's missing as part of this list that needs to pretty much close back to the first vertex. So that means that we need to have an edge between vn and v1. So in this case, because n is 3, we would need to have an edge between v3 and v1. Okay, what about if it's 4? Well, if it's 4, again, we'll call this v1, v2, v3, v4. There is an edge between v1 and v2, between v2 and v3, between v3 and v4, and between v4 and v1. And that pattern simply continues. If now we're considering 5 nodes, it just means that we're going to have edges that connect between two subsequent nodes. So that's a cycle. Now wheels are related to cycles, but before we consider how, let's look at this definition for the union of two graphs. Okay, so let's say that graph consists of vertices v1 and edges e1, And H is another graph that consists of vertices V1 and edges E2. We defined the union of the two graphs as the union of the sets of vertices, comma, the union of the sets of edges, meaning the union will also be a graph. So now that we have that definition, a wheel, which is denoted W sub n, is a simple graph with n plus 1 vertices such that W sub n is the cycle C sub n union with this graph that has V tilde and E tilde as sets of vertices, set of vertices and set of edges respectively. Now what are those sets? The set of vertices is just one additional vertex, V sub n V sub n plus 1, and E hat is the set of edges that connects the node V1 to V sub n plus 1, V2 to V sub n plus 1, and Vn to V sub n plus 1. So in other words, what this is doing is it's introducing an additional node, and then all of the pre-existing nodes, and by pre-existing I mean that are part of the cycle, those are all going to now be connected to this new node. Yep. So let's see what that looks like. We're going to have to start at W sub 3 because W sub n is defined in terms of C sub n, and C sub n is only defined for n being 3 or greater. So we'll look at the wheel with 4 nodes. Okay. That means that we have a cycle with 3 nodes and edges between those nodes, and then we just introduce an additional node. Okay, so this is V1, V2, V3 that are part of the original cycle, and we've introduced this 4th node, which we're going to call V4. Okay, so that would be this one here. And then we need to introduce the edges that connect all of the nodes that are part of the cycle to this new node. And just to give some additional information, I'm going to write what C3 is. C3 is the set of vertices V1, V2, V3 with the set of edges V1 to V2, V2 to V3, V3 to V1. So we took that graph, took the union with V4 and these additional 3 edges to get W3. And let's take a look at what W4 would look like. So W4 is the union of C4, which is the cycle with 4 nodes. So first we'll draw that. And we introduce an additional node. So V1, V2, V3, V4 will be part of the original cycle C4. And then this new node V5 is part of this V tilde that we're creating, along with the edges of V5, V2, V1, V5, V3, V5, and V4, V5. Alright, so that's in general how it works. W5 can be drawn in a very similar fashion. Let's take a look at this next one, n cubes. An n cube, which is denoted Q sub n, is a hyperdimensional graph that has vertices representing the 2 to the n bit strings of length n. 2 vertices have an edge connecting them if and only if the bit strings they represent differ by exactly 1 bit. And so what we're going to do here is maybe show what the n cubes would be for n being 1, 2, and 3. Okay, so let's take a look at Q1. So Q1 means that we're looking at vertices that represent bit strings of size 1. So how many different bit strings of size 1 do we have? Well, that would be 2 bit strings. One of them is a 0, the other one is a 1. And so the graph Q1 would consist of 2 nodes and 1 edge. And the number of nodes has to be consistent with the number of bit strings size 1. Okay, let's take a look at what is Q2. So Q2 is now going to be the number of different, for the nodes, it's going to be how many different bit strings length 2 do we have. And so that would be 4. We can have 0, 0, 0, 1, 1, 0, and 1, 1. And I'm actually going to draw this a little bit differently. I'm going to go ahead and take the 1, 0 and place it here, and the 1, 1 place it there. Now the reason being is that we're going to draw edges between 2 bit strings if and only if they differ by at most 1 bit, or by exactly 1 bit actually. So because 0, 0 differs by exactly 1 bit with 0, 1, it differs in the first bit, there's going to be an edge connected there, connecting those two. Now if we take a look at 0, 0 versus 0, 1, those also differ by 1 bit, which is the second bit, so we would draw the edge there. Compare the 0, 1 with the 1, 1, and they differ only in the first bit. And finally, if we compare the 1, 0 with the 1, 1, those also differ with in 1 bit, so we would draw an edge. And so again, the reason why I switched those was to show you that you can actually create a graph that looks like a square in this case, which is part of the reason why these are called n cubes, because you can actually form squares or cubes in the, well, in whatever dimension is determined by the n. Let's try one more, Q3. In this case, we're taking a look at how many different bit strings size 3 do we have, and that would be 8. So we're going to have 8 nodes. And let's see how many edges that's going to result in. Yeah, so first let's list out what are the different bit strings that we can get. We could get a 1, 1, 1, or a 1, 1, 0, or a 1, 0, 1, or a 1, 0, 0. We could also have a, let's go ahead and write it here. We could have a 0, 0, 0. We could have a 0, 0, 1, a 0, 1, 0, and a 0, 1, 1. So notice the way that I'm listing them here is I'm simply taking this bit string and changing 1 bit, the first one, and changing it from a 1 to a 0. And that's intentional because then I know that there's supposed to be an edge between the 2 nodes that represent these different bit strings. The same is true about these 2 bit strings because they only differ in the first bit. Same thing for this one and this first one. Okay. So all of those are going to have edges connecting them. We can also compare these bit strings on the left-hand column against themselves. So 111 versus 110 has only 1 bit that is different. So there's going to be an edge that connects there. If I compare this bit string versus this bit string, there's actually 2 bits that are different, right? The second and the third. So there wouldn't be an edge between those two. But if I now compare 101 versus 100, these two are different only in the last bit. So there would be an edge that connects them. And, well, since these are pretty much the same bit strings except for the first bit, the same is going to be true about these, right? The 011 is different from a 010 only in the last bit. 001 is different from 000 only in the last bit. And then if we compare these two, they have two different bits in the second and third positions. So we wouldn't connect an edge there. And then, well, we just want to double check if we compare, because we've compared it pretty much whatever bit string we have side by side, but we should also compare like 111 with the third bit string on the left hand side, 101. In this case, they're only different in the second bit, so those two would be connected by an edge. And if I take a look at 110 versus 100, those are also just different in the second bit. So there would be a connection between those two bit strings. Or there would be an edge between the nodes that represent those two bit strings. And the same is going to apply on the right hand side. We're going to have a connection there. Again, you can go ahead and verify 011 is different from 001 just in the second bit. 010 is different from 000 just in the second bit. Right. Now those are all the connections that we can find. So now we're going to draw the graph. And what I want you to notice is the fact that there is an edge between 111 and 011, a connection between 011 and 010, connection between 010 and 110, and then connection between 110 and 111. So basically what we're noticing here is that if these were the actual nodes, there is a square going on between those four bit strings. There's also a square going on between these four bit strings. So we're going to have a first square and a second square. We're also going to have connections between the first square and the second. Right? We're going to have one that connects the top of the first square with the top of the second square. And the top of the, well, I should say the top left. We're also going to have something that connects the top right of the first square with the top right of the second square. And the bottoms will also see something similar. The bottom left-hand corner is going to be connected to the bottom left-hand corner of the second square. And same thing for the right hand. So if we were to draw that, it would look like this is going to be the back square that has 111, 010, 011, and then 010 and 110. And we said we have connections between all four of those nodes. Then we said we also have the second square, and I guess I can color code it differently, that way we can distinguish between the two. So this is the back. This one we're going to call the front. So again, we're going to have four nodes. We'll have a 101, a 001, a 000, and a 100. And those are all connected in a cycle like this. Okay. And then we have 1, 1, 1 connected to 1, 0, 1. So that's this connection. We also have 0, 1, 1 connected to 0, 0, 1. So that's this connection. And finally, we have 1, 1, 0 connected to 1, 0, 0. And 0, 0, 1, 0, 1, 0 connected to 0, 0, 0. Now for example 1, they're asking us to draw some additional graphs, starting with case 7, which means the complete graph with 7 nodes. So what I'll do is I'll draw the 7 nodes. Kind of in this shape. And we said for a complete graph, it means that there is an edge connecting every distinct pair of 2 edges. So let's just say I'm going to label these A, B, C, D, E, F, and G. If I think about what I can connect A to, well, I can connect it to B, C, D, E, F, and G. And now that node is fully connected to all the other nodes. Then we can move on to B. And B is already connected with A, but now we can connect it with C, D, E, F, and G. Okay, then we move on to C, which is already connected to A and B. Now we can connect to D, E, F, and G. And we just repeat that process. So moving on to D, we can connect it to E, to F, and to G. Moving on to E, we can connect it to F and to G. And then moving on to F, we can connect it to G. So that would be the complete graph for 7 nodes. Now for part B, they want us to find the cycle with 7 nodes. So it's going to look, I'm going to draw the shape similarly. And the outer part will look the same, we just won't have any of the inner edges. Okay, so this is A, B, C, D, E, F, and G. So it'll look something like that. And that would be our cycle. Now for C, we have the wheel with 7 nodes, which is going to be pretty much the cycle with the 7 nodes and then the additional vertex at the center and all the edges that connect to it. Okay, so for W7, let me draw the 7 nodes. Okay, so there's 7 nodes and the additional middle one, and then we'll have all of the nodes connect to that additional node, and that would be our W7. Okay. Example number 2 is asking how many vertices and edges does the graph Q4 have? So Q4 is the 4 cube, which means that we're considering bit strings of length 4. Okay, so the number of vertices is going to be the same as the number of bit strings length 4. So let's just go ahead and write that. So number of vertices is equal to number of bit strings length 4. And that's going to be a 2 to the 4th, which is 16. We have 16 nodes. Now for the number of edges, you could do this using combinatorics and counting. But I'm going to go ahead and list out all of the possibilities, all of the possible bit strings, which would be represented by nodes in the graph. And then we'll see where all of the connections are, and we'll count those connections. Okay. And part of the reason why I'm doing it in this way is because I want to show you that it gets pretty complicated pretty fast, and it's not something you can easily draw. In fact, because this is now in 4 dimensions, we wouldn't technically be able to draw it as a cube in the 4th dimension. So there are ways to represent that cube in well, just in a 2-dimensional plane on our paper, but that looks nothing like a cube. So I won't be drawing it here, but like I mentioned, I am going to list out the different bit strings that we can have and the connections. Okay, so I'm starting with bit string of all zeros, then 3 zeros and a 1. Then I'll still have just a 1. I'll have 0, 0, 1, 0, so I'm just going to swap the order of those. And then I'll have a 0, 0, 1, 1. Okay. And all of these nodes, all of these bit strings are going to have connections between them, except for these middle two, because these are different in 2 different bits. So that means that we'll just have these 2 connections plus some of these outer ones. So 0, 0, 0, 0 is different from this 3rd bit string at just 1 bit, the 3rd bit. So there's going to be a connection here. Then 0, 0, 0, 1 is different from a 0, 0, 1, 0, 0, 0, 1, 1 at the 3rd bit as well. So there would be a connection here. Now, if I go ahead and replace this bit, the 1st bit, into a 1, but keep the rest of the bits the same, then I'm going to form edges between these bit strings on the left-hand side and the new bit strings that we create on the right-hand side. So let's go ahead and do that. Those are all going to be connected, and while using the symmetry of, yeah, pretty much, the symmetry of the edges that we found, we're going to have edge between the 1st and the 3rd bit string. We're also going to have between the 2nd and the 4th, and then between the 1st and the 2nd, and between the 3rd and the 4th. Okay, now these are not all the bit strings, it's only half of the story. We could also have 0, 1, 0, 0. Okay, where now I'm switching the 2nd bit from a 0 to a 1. And that means that we could have a 0, 1, 0, 1, a 0, 1, 1, 0, a 0, 1, 1, 1. And so because the only thing that I did to get these bit strings from these at the top was switch the middle bit to a 1, all of these are going to be connected. Right, so we're going to have connections that look like this and like this and like this, right? So 4 connections. Now we'll repeat the process that we did earlier, which is now switch these the 1st bit from 0 to 1, keep the rest of the bits the same. And we'll have these edges connecting those bit strings. We'll have, and here I still haven't listed these connections that happen between these 2 adjacent bit strings. So these would have a connection, these would have a connection, this is going to have a connection, and this is going to have a connection. Same thing on the right hand side. These two are only different on the fourth bit. These two are only different on the fourth bit. The first and the third are only different on the third bit, and the second and the fourth are only different on the third bit as well. And now, if you take a look at the bit stream 1000, compare it against 1100, they're only different at the second bit. So we're going to have a connection here. We're also going to have it between 1001 and 1101. And basically, we're just going to see these four edges also happen on the right-hand side. So let's count how many edges those are. Here we have 4. At this level, we also have 4. At this level, we have 4 as well. Here we have 8. Okay, here we have 4. Here we have 4. And here we have 4. Okay, so that's a 12. So that's a 24 plus an 8. That's going to give us a 32. So what that means is that the number of edges is 32. We're now going to take a look at bipartite graphs, starting with the definition. So a simple graph G with set of vertices V and set of edges E is called bipartite if there exist non-empty sets V1 and V2 such that all of these are true. So V1 intersect V2 is the empty set. So what this means is that they are disjoint. If the union of V1 and V2 gives you the set of all vertices, if for every edge Vi, Vj, that is part of the graph, Vi is from the first set, V1, and Vj is from the second set, V2, and there exist no edges U, V in the graph such that either they're both of the nodes are in V1 or both of the nodes are in V2. So what that means is that there are no edges connecting the vertices in V1 amongst themselves, and the same can be said about V2. Okay, so that's what it means to be bipartite. And so just to draw maybe kind of like a diagram here, if this is V representing all of the nodes that are part of the graph, we're basically finding a subset, call it V1, and a second subset, call it V2, such that the graph only has edges between the two sets. Okay, so maybe something like that, but not amongst themselves. Alright, if a set is bipartite, then we call the pair V1, V2, so the two sets, a bipartition of the set of vertices. Yeah. And then one last definition, a complete bipartite graph, which is denoted as K sub n, n, is a bipartite graph, so it's going to satisfy all these four conditions, such that the set E consists of all possible edges between V1, between nodes in V1 and nodes in V2. And here these M and N, M is the size of the first set, V1, and N is the size of the second set, V2. Alright, so let's apply these definitions. Example 3 reads, are the graphs G and H bipartite? If so, are they complete bipartite? Okay, so let's take a look at G first. Bipartite means that we can separate the nodes into two different sets such that all of the nodes in the first set are only connected to nodes in the second set and not amongst themselves. Okay, so let's start by taking a look at node A. And we'll place it in, we'll say V1. A is connected to C, E, F, and G. So that means that C, E, F, and G, if this graph is bipartite, would have to be in the second set of vertices. So I'm going to start creating that. we'll have C, E, F, and G. All right, now let's move on to B. B is connected to C, okay, and C is part of V2. So that means that A would need to be, that means that B would have to be part of the first set, V1. Okay. And that has to be consistent with E and F being part of the second set, right? Because these two cannot be part of the same set. So F and G would have to be in the opposite set to B, which is consistent, right? We see E and F in V2. Okay, now let's move on to node C. C has 3 connections, A, B, and D. That means that if C is already in V2, A needs to be in V1, which it is, B needs to be in V1, which it is, and D would have to be in V1. Okay. All right, let's move on to node D. D has 4 connections. It has connection to C, so C has to be opposite the set where D is located, which is so far so good. Then G has to be in the opposite set, that looks good. F has to be in the opposite set, and E has to be in the opposite set, all of which are consistent so far. We'll move to E. E has 3 connections, A, B, and D. So that means that A, B, and D have to be opposite to E, and they are. They're in the different set. F has connections to A, B, and D. Okay, here's F. A, B, and D are in a different set, so that looks good. And finally, G is connected to A and D, so that means that G and A and D have to be in a different set, which is consistent. So because we are able to partition the set of vertices into these 2 sets, such that the edges are only between nodes of different sets, then this is bipartite. Okay. Is it complete bipartite? So complete bipartite means that the graph contains all possible edges between the two sets. Okay, so between the sets of the bipartition. So if we take a look at A, all possible edges that have A would be A with C, A with E, A with F, and A with G. So we see here A with C, A with E, A with F, and A with G. So far so good. Then we take a look at B, and B would have to have all of those same edges. B with C, B with E, B with F, B with G. There is a B with C, there is a B with E, there is a B with F, but there is no B with G. Right? So because B with G is not part of the graph, then this is not a complete bipartite. Okay. All right, so this was for G. Let's take a look at H. Okay, so for H, again, I'll start at node A. A is connected to 3 nodes, B, E, and F. So if we place A in V1, that means that in V2, we have to place B, E, and F. Okay, we now move on to node B, and B is connected to 4 actually more than 4, it's actually connected to 5 different nodes. It's connected to A, so that means that A and B have to be in opposite sets. It's connected to F, which means that B and F have to be in opposite sets, but we actually see it F and B be part of the same set of V2. So that means that this is not bipartite. Okay, so we'll go ahead and write this justification after we state this is not bipartite. Because A, comma B being an edge in the graph forces A to be in V1 and B to be in V2, but we also have the edges B with, we said, F and A with F. So because there is an edge between two nodes that are part of the same set of vertices, this is not bipartite. Okay, we're going to take a look at a theorem now, theorem 1. It says a simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex of the graph so that no two adjacent vertices are assigned the same color. Okay. And then for example number 1, they want us to use theorem 1 to determine whether graphs in example 3 are bipartite. Okay, so we already know which one is bipartite and which one is not. So essentially what we're doing is just verifying the theorem and against our results. Okay, so let's start with G. What I'll do is I'll color code the node A as green, and then A is connected, we said, to 4 nodes, to C, E, F, and G. So all of those are going to receive a different color because we want edges to have 2 nodes of different color. Okay. Then because C is blue and it's connected to B, that means that B needs to be green. Okay. And green is now connected to blue and connected to blue there as well. So these 3 nodes are consistent so far with the requirement. And finally D. D is connected to G, connected to F and E and C, all of which are blue, which means that D would have to be green. Okay. And so since all of the edges have 1 blue node and 1 green node, then this is bipartite. Okay, let's take a look at H now. We'll go through the same process. I'll start by color coding A green, and then A is connected to B. It's also connected to E, and it's connected to F. Okay, now in this case, we already see a violation. There is 1 edge with 2 nodes of the same color. In fact, not just 1, but 2, right? B with E and B with F. So that means that this is not bipartite. Example 5 is asking us to determine whether each of the following graphs are bipartite, and if so, we want to give a bipartition of the set of vertices. So let's start with the cycle with 6 nodes. I'll call this V1, V2, V3, 4, 5, and 6. And we'll start at V1, color coding it green. Then since V1 is connected to V6 and V2, those are going to be blue. Then V2 is connected to V3, so that'll be green. V3 is connected to V4, so that'll be blue. And finally, V5 is connected to both V4 and V6, which are both blue, making V5 green. And so, since we have all edges consisting of nodes of opposite color, that means that this is bipartite. And we're going to give a bipartition. It will have V1, the set, not the node, consist of maybe all of the green nodes. So we'll have V1, V3, V5. And then V2 is going to consist of all of the blue nodes. So that'll be V2, V4, and V6. Okay. All right, what about K3? So remember, K3 is the set of, it's the simple graph that is connected. Okay. That is complete. So we'll start V1, V2, V3, and V1 can connect to V2 and V3. V2 can connect to V1 and V3, and then V3 can connect to, well, V1 and V2, and those are already connected. We'll start by color coding V1 green, and V2 would have to be blue because V1 is already green. And then V3 and V2 are connected, so that would mean that this has to be green. But then we see that we have one edge with two nodes the same color, so this is not bipartite. Okay. And one more example. They want us to draw the following complete bipartite graphs. So remember, complete means we have, it's going to be bipartite, and we're going to have all possible edges between the two sets of nodes. Okay, so K2, 3 means that our first set of vertices, V1, has two nodes in them, so let's just call them A and B. And the second set of vertices has 3 nodes, so we'll call it C, D, and E. And to draw the graph, let me just first draw the 2 nodes that are part of V1 and the 3 nodes that are part of V2. This is A, B, C, D, E. And because this is bipartite, let's go ahead and color code. Okay, so the nodes that are part of V1 will color code green, and the rest will color code blue. And that means that green will only ever connect to blue. Okay. So all possible edges between A and blue nodes would be A with C, A with D, A with E. Then repeat the process for B. And that would be K2, 3. Now for K33, I guess I should label. Okay, for K33, that means that we have the first set of vertices with 3 vertices, so A, B, C. And then the second set would also have 3, so that would be like D, E, F. And we'll have A, B, C, D, A, B, C, and then D, E, F. All the nodes that are part of V1 will color code green. All the nodes that are part of V2 will color code blue. And we only want green connecting to blue. And we want all possible edges. So between A and blue nodes, we have AD, AE, AF, then BD, BE, BF, and CD, CE, CF. And that would be K33. And we have one more, K26. So that means first set contains 2 vertices. We'll call them A and B. Second set contains 6. So we'll have C, D, E, F, G, H. Alright, so A, B, and then we'll have C, D, E, F, G, H. Okay. And similar process, A and B are part of V1, so we'll color code that green. And the rest will be blue nodes. Okay. So then for A, there are 6 possible edges. And for B, there will also be 6 possible edges.